less than 10 seconds.
Hey everyone, Michael here from the HR MacMillan Space Centre. Once again, joined by Let's Talk Science Morgan, who is not in her home. She is actually out at UBC in the lab doing work, taking time out of her busy day to share with you. How's it going, Morgan?
Good, good. How are you?
I'm doing great. So tell us, you were doing some experiments in the lab, and you actually, as we were coordinating this meeting, you said that you couldn't meet at certain times because you're checking on an experiment that's running right now. Do you want to tell us a little bit about it?
Yeah, I hate to be that annoying person, but basically when I'm in the lab, my availability is not every half hour. So on those half-hour marks, what I have to do is monitor the bacteria that I'm working with and make sure it's growing or not growing, depending on exactly what we're doing.
That sounds really fun. As you're doing some of these experiments, we're going to transition into thinking about the future of rockets. And you got a really fun activity for us this week. Why don't you tell us about it?
Yeah, so we're just looking at a little bit more sophisticated of a rocket than we looked at last time, which is kind of like rocket evolution if you watch both videos back to back in a weird sort of way. And so it's one of the classics. We're just erupting a rocket or fueling a rocket with baking soda and vinegar, which I'm sure you've seen once or twice before. It's not as easy as you think it is. It took a few takes and I still didn't nail it. But that's fine. People at home will.
Well, it's all about the process, right? Like you try some things out and you experiment and you have fun, just like you're doing right now, right, Morgan?
100%, definitely. And the more
Awesome.
times it blows up in your face, the more fun you will have.
Okay, all right. Well, hopefully everyone out there is doing their experiments safely. Please send us a message or videos. We'd love to see some of your videos on the future of rockets. All right, Morgan, it's almost at the half-hour mark, so you should probably check on that experiment. Take care, everyone. Have fun.
Enjoy.
Hi everyone, I'm super excited to be back this week talking about the future of rockets. If you've been kind of riding along with us for the last few weeks, you'll know that we did a rockets episode previously where we built a really simple rocket launcher that relied on the use of air pressure in order to launch a paper rocket. Today we're going to be doing something slightly more sophisticated, one of the rocket experiments that is really a crowd pleaser. The parents and kids tend to love it when we do it at community events. And this one is slightly more sophisticated in the sense that we rely on the buildup of water pressure or fluid pressure from liquid, and we launch a plastic rocket off of its launcher. You're accustomed to seeing chemical rockets engines that burn their fuel to generate thrust. Although this is exciting, there are many other ways to generate thrust, and it's something that's being actively explored in the future of rocket engines to make rockets less polluting, more sustainable for our environment. Any system that throws mass would do. If you could figure out a way to accelerate baseballs to extremely high speeds, you would have technically a viable rocket engine. The only problem with that approach would be that the baseball exhaust left streaming through space, again, is kind of polluting and defeats the purpose of the research of using alternative methods for fueling rockets. This small problem caused rocket engine designers to favor gases for their exhaust product. Many rocket engines are very small. For example, attitude thrusters on satellites don't need to produce much thrust. One common engine design found on satellites uses no, quote, fuel at all, but pressurized nitrogen thrusters that simply blow nitrogen gas from a tank through a nozzle. Thrusters like these kept Skylab in orbit and are also used on the shuttle's manned maneuvering system. New engine designs are trying to find ways to accelerate ions or atomic particles to extremely high speeds to create thrust more efficiently. NASA's Deep Space One spacecraft was the first to use ion engines for propulsion. Other interesting endeavors are also being assumed by NASA. NASA selected SpaceX to develop a lunar-optimized Starship to transport crew between lunar orbit and the surface of the moon as part of NASA's Artemis program. A lunar-optimized Starship can fly many times between the surface of the moon and lunar orbit without flaps or heat shielding required for Earth return. With large habitable and storage volume, Starship is capable of delivering significant amounts of cargo for research and to support robust operations on the lunar surface to enable a sustainable moon base. Last year, NASA announced Starship is eligible for the Commercial Lunar Payload Services Initiative to deliver payloads between Earth and the Moon and to enable humans to return to the Moon, possibly equipping us for human spaceflight in a commercialized manner very quickly. So the first thing we want to do in order to build our water-powered or fluid pressure-powered rocket launcher is collect all of our materials somewhere outside, because this could be a little bit messy. So you're going to want a plastic bottle. The smaller the plastic bottle, the better, I've found in my experience. You can use something larger. It's going to require more vinegar and more baking soda, but might give you a little bit more of a explosive liftoff. Explosiveness is definitely also achievable with a smaller bottle, just a little bit less messy. You're going to want some white vinegar. We are not sponsored by Allen's, but perhaps we should be, because we do a ton of these rockets at our community events. Like I said, really popular. You're going to want some tissue. You can use toilet paper, tissue paper for gifts, paper towel, and baking soda. Again, not sponsored by Arm & Hammer, but we should be. Alright, so I'm going to use the smaller bottle for our demonstration today, and the first thing I'm going to do is measure out how much vinegar and how much baking soda I need. So for a 250 milliliter bottle, we suggest filling about halfway. Usually this is about an inch or so, but this is going to be different because I've got kind of a tall skinny bottle here today. So I'm just going to kind of eyeball it. It doesn't have to be exact. So now we've got our vinegar open, we're just going to pour it into the bottle. You can use a funnel, again, if you're working somewhere you want to make less of a mess. Alright, so that looks pretty good. Next, we're going to measure out our baking soda. So, like I said, for a 250 milliliter bottle, about 2 tablespoons. And I'm just going to kind of eyeball it here because I've done this a zillion times. And then what you want to do is roll up the tissue paper very tightly so that no baking soda really leaks out, and so that you are also able to fit it into the nozzle of your bottle. So then once I've got this rolled up, I'm going to put it into the top of my bottle, put the cork on my bottle, and turn it upside down. And I'm going to try to work very quickly because the chemical reaction is going to start happening, and we're going to have a rocket explosion. Wasn't fast enough. That's a good one. So what's happening when we're mixing the baking soda and the vinegar? There's a lot of bubbling and foaming, and that has to do with the chemistry behind the reaction that occurs between our vinegar, which is acetic acid dissolved in water, our acid in this case, and the baking soda, which is sodium bicarbonate, our base. So basically what happens is they form a very unstable intermediate that is quickly broken down to carbon dioxide and water, and the carbon dioxide forms the bubbles that we see in our liquid. This bubbling generates a lot of water pressure, which when we put a cork on top of the bottle builds up to a certain point where the cork can no longer handle the pressure, and whoosh, we get an explosion. And that's what allows our rocket to take off, is that sort of explosiveness that shoots the cork out of the bottle and then propels, using the thrust generated from the cork, propels the bottle up into the air for space flight. Of course, we didn't quite get there in mine because, as you can see, the chemical reaction doesn't take long. I can't bring myself to do a second take because I have a feeling it's just going to turn out much the same. But hopefully you guys are able to work quickly enough. Perhaps you have a partner at home that can help you out with your experiment and get the bottle the right way up quickly. Let us know what you guys end up with. Send us in some pictures of the rockets that you design. Hopefully they're much more better looking and you end up painting and using some cardboard paper. And tune in again next week.